wish I had some of this. Bloop. Okay. Science time. We are talking today about forces, so please title this Forces. You may not believe this, but you're going to have to because I'm going to tell you. Let's do it in blue. This is the second time that I have talked about forces today in class and on video, but we're going to do the same thing that one did. Here I've got the word forces writ large. Forces. We're talking about forces today, and as someone said, who was it? Caden said that a force is a push or a pull on an object. So let's write that down. Push or pull. That is intentionally vague because one of the things that vaguity does is it encompasses a lot of things. The objective we have is to model forces. So let's also write that down. I assume that's already written down on your lab. Is that true? Model forces. Remind me, what's a model? Okay, yes, systems can be modeled. Yeah, not necessarily smaller. Think about like a model atom. That's a lot bigger than an atom. So no, it doesn't have to be even. It does. It's very little to do with the size actually in definition. Let the man think. It's okay. Isaiah.
A model is a simplified, imperfect representation.
Yes, a simplified. Although, if we're going to yell at, no one yelled, but if we're going to be slightly mean to Trey about saying that a model of an atom is actually larger than the atom, we probably shouldn't say it's simplified, but it is a representation, and it's an imperfect representation, right? And so when we model forces, we're going to represent forces. Probably, maybe, with a diagram, and there will be some modeling of forces in this. Teague, would you hop up and get the door, please, now that Kindle's back? So a force is a push or a pull on an object, and today we're going to model, that is, diagram some forces. A force is any push or a pull on an object? Would you be willing to go that far to say it's any push or a pull on an object? If I push on this wall, is that a force? Yes, okay, that's correct. But the wall's not moving, right? So is it a force even if it doesn't cause something to move? Yes. And one of the ways that we break up forces is into balanced or unbalanced forces. Balanced or unbalanced. So forces can be balanced, meaning that two or more forces on an object can effectively cancel each other out. Let's start by drawing a model. Give me an object that you think I can draw. Give me an object you think I can't draw. That'll be more exciting. Dog! Okay, thank you. Let's draw Justice's dog.
That's a court.
I know, I'm trying. Give me a second. I'm not even done yet, am I? Are their tails cropped? I can't remember.
Yes,
Oh, the deer actually is wrong.
yes, you do.
It has the tail, but it's tiny.
No, he has a big tail.
This is a pig. Shut up. I'm drawing a pig. Okay. There we go. Yeah, really. Okay.
Yes, bro, that's what we're talking about.
Okay, a pig! I've drawn a pig. Let's say the pig farmer, which this is what he looks like. He's got a hat because he's a farmer, obviously. The pig farmer wants to push the pig along, and so we indicate that with an arrow showing the direction and relative strength of the force, right? The direction, indicated by the direction of the arrow, and the relative strength, meaning how strong it is relating to some other nominal force, as the length of the arrow. The longer, when we draw a diagram like this, when we draw a model like this, the longer the arrow we draw, the stronger the force, okay? So in this case, the farmer is putting a force of a certain magnitude on this pig, okay? So far, so good. You with me so far? On the I'm not going to say the right, the classic way to diagram forces is with an arrow originating at the center of mass of the object. And the longer the arrow, the stronger the force. What could we label this force? What kind of force would you call this? A push, yeah. So I'm going to label F sub push. So F, and then in little letters below it, push, the push force, okay? Are there any forces opposing this push? Does gravity, let's rewind a little bit. Is gravity acting on the pig? Most likely, right? In normal situations, there is also gravity acting on the pig. Do you think the gravity acting on the pig, by the way, that's called weight. Weight is the force of gravity acting on an object. Do you think the gravity acting on the pig is stronger or weaker than this push force?
Weaker.
Sure, let's say weaker. And which direction does gravity act?
Down.
Always down. So we're going to draw the arrow a little bit shorter. We're going to draw it down. Is anyone else going to do this too? The picture is not just for my benefit. This is part of your notes. And what should we label this arrow? F sub gravity, yeah, F sub G, or we can also label it W. What do you think W stands for? I've already said. Weight. Thank you. Hunter, you're doing a great job being an 8th grade scientist today. Okay, we're not done. I'll tell you that for free. We're not done. Is there anything preventing the pig from falling down? Because if this is true, the pig is moving down and to the right. Is that what's probably going on in this scenario? No. The normal force, Justice, a graduate of physics class, says that the normal force, so the meaning that, why did I just draw that just now, do you think? What does this line probably represent in models? The ground. And the ground provides an upward force to resist gravity to the same magnitude, but we call this F sub capital N, the normal force. Now check it out. Let me give you a real life example. Not with a pig because I don't have one, but with this little guy. You see him? Okay, please stay put. Pretend it's staying put. Are there forces acting on this right now? It's not moving. Is there a push and a pull, or a push or a pull acting on this? Teague says no. Aiden says yes. Isaiah says yes. Trey is nodding. What force is acting on this, do you think? Gravity. Is gravity still acting on it even if it's not moving? Yes. And why is it not moving? So let me ask this question in a more basic way. Can an object have forces acting on it, but its motion isn't changing?
Yes.
It's not moving or it's not changing its motion. Sure. That's when the forces are balanced. So in the case of the gorilla, there's gravity pulling it down and the normal force provided by the podium pushing it up. And those two are opposite in direction, but they're equal in magnitude, so they cancel out. They both still exist. They're not actually canceled. They both still exist, but they're balanced. So in the case of balanced forces, what could we say is true of balanced forces? When only balanced forces act on an object, what? Not necessarily. That's correct. I wish someone other than Hunter, a junior in high school, had said it, but that is correct. Its motion doesn't change. That's something extremely important for you to write down. When only balanced forces act on an object, its motion doesn't change. Let's do a trick. Close your eyes. Wait, unclose your eyes. That is open your eyes. Check out this gorilla. Do you see the gorilla? Ethan, you don't see him. I can tell because your eyes aren't over here. Do you see the gorilla? Rhett, do you see the gorilla? Do you see the gorilla?
Yep.
Does anyone not see the gorilla? Now close your eyes. Okay, this is a good trick. Now open your eyes again. Did the gorilla move? No, it didn't. Because only balanced forces are acting on it. Okay? Here's another trick. Close your eyes. Wait. First look at the gorilla again, or just remember how it was before. Close your eyes. Everyone close your eyes. Now open them. Also, I knocked the lid off my marker because I got too excited. Where did the gorilla go?
Right there.
Yeah, okay, it's over here by Alana's backpack. But did its motion change?
Yes.
Yes, its motion changed. How do you know? You didn't see it move. How do you know its motion changed? Kendall said it right. Kendall said it almost the way I want you to say it. She says, say it again, Kendall. It's in a different spot. I wish the only problem is not really a problem. The only difference I would make is that I wish she said position. But motion is a change in position, right? So an unbalanced force must have acted on that because its motion changed. Unbalanced forces cause a change in motion. And we, as a little side note here, I've kind of run out of room, I've trapped myself, but motion we can define as a change in position. Okay? Now, back to our pig. The way this diagram is, the way this model is representing right now, are the forces acting on this pig balanced or unbalanced? Okay, so we've got gravity down, the normal force up, and the push force. Unbalanced, right? Gravity and the normal force cancel out. Gravity and the normal force are equal in magnitude but opposite in direction, and so they are balanced. But there's this push force in the horizontal direction, meaning that it has unbalanced force on it. So will the pig's motion change? Yes, the pig's motion will change. The pig's motion will change. And we'll get to this in the next lesson, but in what direction will the pig's motion change? If the force is acting right, how will the pig's motion change? We don't know what its motion was like before, but its motion will change rightward. There's a name for this change in motion. Change in motion, not to be confused with motion itself. Remember, motion is a change in position. That's over here. A change in motion is called, does anyone know from your vocab, what's a change in motion called? You should know from your vocab. Acceleration. That almost came into contact with my other definition. So motion is a change in position, and when motion changes, that's called acceleration. Because this pig has an unbalanced force on it, it will accelerate. We can say it that way. Its motion will change, it will accelerate. There are 3 ways an object can accelerate. Give me the easiest one. What's the easiest one that everyone knows that an object can accelerate?
Push.
Sorry, let me rephrase it. I'm not talking about the causes of acceleration. I mean, in what ways can an object's motion change? That's not really a better way of describing it. It can go faster. Let me give you that one. That's easier. It can go faster. What else could it do? Go slower. Now, be careful, because the joke I keep making is, to the trucker, acceleration only means go faster, right? I shouldn't even just say a trucker. To a layperson, to a police officer, acceleration means go faster. The gas pedal in a car, you call it the gas pedal. Some people call it an accelerator. Some people call it a throttle. But that word accelerate in the colloquial speak means go faster and only go faster. But to the physicist, acceleration is any change in motion. And so another way an object can accelerate is to go slower. We might, in our daily life, call that decelerate, but that's not a physics word. They're both kinds of acceleration. What's another way? This is the one that people often don't get. What's another way that an object's motion can change? No, that would be going slower. Stopping is going slower. Nope, because it wouldn't be accelerating, right? If it's at rest, it's not changing its motion.
Maintaining.
It could be. Okay, almost, Hunter. Say a better verb. What? Direction. Who said that? Good job. Changing direction is the other one. So even if it's going the same speed, and it changes direction, that's an acceleration. Because is that a change in motion? Yeah, maybe it was going, think about this curve on the highway right outside of Crawford. The speed limit there is 65 miles per hour. Maybe and your mom's driving and she's going 70 miles per hour north. The cruise is set, and then she goes around that curve. Now she's still going 70, but she's going east, right? So that's just it didn't go faster or slower, but the direction changed, and that is acceleration. That's a change in motion. Does that kind of make sense to you? One of the ways that you can think about this is that these three kinds of changing motion, you can feel them. Your body, one of the things your brain does instinctively is act as an accelerometer. That is something that measures acceleration. You can feel, even if your eyes are closed and you're in the car and your mom's driving, you can feel if she speeds up, right? You could feel that. You could feel if she slows down, and you could feel if the direction changes, even if neither speeding up or slowing down, right? Right? So those are the ways that an object can accelerate. And what causes acceleration? Not just any push force. It has to be
Motion.
What kind of force? We've talked about two kinds of forces. Which one causes a change in motion? Unbalanced force causes change in motion. Balanced force, the motion doesn't change. What are the ways that an object is not accelerating? Not accelerating. Balanced, yes. So the forces must be balanced. There are two things an object can be doing where it's not accelerating. One, like the gorilla now, or even like the gorilla before. The easy one, it's not accelerating. It's sitting there, chilling. What would the physicists say? At rest. One is at rest. That's the easy one. Can anyone get the other one? What other way is an object? Yes, not accelerating. No?
Balance.
Okay, balanced forces, yep. Can it be moving at all and still have only balanced force on it? Let me ask it this way. Can it be moving at all but still not be changing its motion?
Yeah.
Yeah? If it's moving in a?
Direction.
Okay, one direction, right? Like the band.
Forever.
Straight line. Constant speed. So like your mom driving on the highway, cruise set, straight line, constant speed, there's no acceleration. Balanced forces. So let's make the pig do that. So we have back to our pig model. We see that the vertical forces, the normal force and gravity, are canceling out, right? They're balanced. What could be balancing this push force the farmer is providing, such that the pig is only moving at a constant speed in a straight line? What force might be going against the push force? You should know this from your lab. What's it called? What force opposes motion? Friction. So if we say it has just as much friction, we abbreviate that F sub, this is supposed to be a lowercase f. I drew it kind of fancy, but that's the friction force. So in this case, just from this diagram, are the forces balanced or unbalanced? Balanced all around, right? In the up and down axis, in the y-axis, the vertical axis, gravity and the normal force cancel out, right? Gravity's pulling down, the ground is pushing up, canceled out. And in the x-axis, the horizontal axis, the farmer's pushing it, but friction is resisting that push. Can we tell from the diagram, is this pig moving? Nope. We can't tell whether it's moving or not, but we can tell it's not changing its motion. It's not accelerating, right? So what are the two things this pig could be doing? It could either be sitting completely still, or it could be moving a straight line at a constant speed. Balanced or unbalanced? Balanced. Balanced or unbalanced? Just sitting here. And how can you tell?
It's not.
Not because it's not moving, because it's Because it's not changing its motion, right? Now,
Unbalanced.
unbalanced, right? Its motion is changing. Why? What's changing? Is gravity getting stronger and weaker on it? No. What's changing? I'm moving it. I'm changing the normal force on it. Okay? As a little, sorry, I almost missed this. There's another way that we can break up forces. So this is not separate categories from these. It's just a different way of categorizing. Like, we could line up all the 8th graders in order of height, right? Or we could line them all up by shirt color. But it's not a whole nother set of 8th graders with different colored shirts. It's just a different way of categorizing them, right? We can categorize boys versus girls, brown hair versus blondies, and trades off over somewhere else by himself. But we can break up things in different ways, right? Do you recognize that we can categorize things in different ways? So these are not other categories like balanced and unbalanced. It's a new type of categorization. In fact, I'll probably erase this if it's okay. Is anyone still using the stuff that's on the board right now? Raise your hand if you are still using the stuff on the board right now. Yeah, right, Justice. Okay, so a separate way to categorize forces is contact and non-contact. These are vocab words too, I believe. What do you think these mean? As I say, they are vocab words. What do you think they mean?
Is that contact or contract?
Touch. Remember, a force is always a push or a pull. So contact is if the objects are touching. And non-contact is if they are, or yeah, not necessarily. We'll put that.
Interact.
Like I have this magnet. This is a magnet. Do you see that this is a magnet? Got a little shiny bottom on it. Right. Magnetism is a non-contact force, meaning it acts even if the objects are not touching. So if I leave this off the board and drop it, hopefully the magnet will pull it to the board. It does a little bit. You see? So I'm not like, well, that time it didn't, but I'm going to break my magnet if I'm not careful. Right, if I let go of it, well, that was a pretty good one. Do you see that? Like, it doesn't have to touch the board for the force to work. But is it still working right now? Yeah, it is touching, but we still count magnetism as a non-contact force. Similarly, let me pick my gorilla back up. Gravity is a non-contact force. Is this touching planet Earth? No, but planet Earth will still pull it down. Non-contact, right? So not necessarily touching. So examples of this: magnetism and gravity. What are some forces that do require touching?
Gravity. Oh, required touching?
Yep, some forces that do require touching.
Normal force.
Yeah, okay, so the normal force, not just a regular force, but one specifically called normal. Remember the one that's provided by a ground or a surface pushing up on an object. Normal, yeah, what we might call the push or pull force. A normal contact push or pull. What else? Regular, I should have said, contact push or pull. What else? Another very important one that we've already talked about.
Friction.
Thank you. Friction, yeah. Friction, they have to touch in friction. So let's kind of bring it all together. Let's draw one more model. What is another thing I probably can't draw besides Justice's dog, which turns out is a pig? Shark. I bet I can draw a shark.
You have inspiration right now. Yeah, exactly.
Oh, well, I've kind of started my own thing already, so. Look how happy he is. Okay, there's a shark. I like that you picked shark because it's an underwater critter. So let's draw some forces on it. Okay, let's. Does gravity act on the shark?
Yep.
Even if it's underwater?
Yep.
So I'm going to remember about its center of mass. I start drawing arrows. What do the arrows represent? Remind me. Ugh. What do the arrows represent? Yes. What's up? Would an 8th grader please try to answer some of these questions? Forces. If I draw a force down like this, that's going to represent gravity. F sub g. Let's say we think is a reasonable weight for a shark. Let's say it's 1,000. What? What's the unit I use for forces? Not justice. Well, you probably don't know either. What's the unit I use for forces? Newtons. Thank you, Isaiah. The force of gravity we'll say is 1,000 newtons. What force is holding him up? Him or her up? It's not the normal force in this case because the shark is not resting on a surface. It's kind of suspended in the ocean. Does anyone know what that force is called? You might have heard it before. Buoyancy. Yeah, the force of buoyancy. And we'll say that one is 1,000 newtons too. F sub capital B is buoyancy, and we'll say that's also 1,000 newtons. So as it is right now, are the forces balanced or unbalanced on this shark? Balanced. What do they add up to? 1,000 newtons up plus 1,000 newtons down equals what? 0. Because one of them could be negative, right? If we called them up and down, but that's the same thing as negative and positive. So the net force, we call it, the net force is 0. And that means what? We call it balanced. Right? Now I'm going to change colors because that's going to still be true in the blue. Where did my lid go? Does anyone see my marker lid around here somewhere? Oh, thank you. Perfect. Okay, now let's say there's fluid friction acting on him or her to the effect of, so the force of friction, and we'll say that's going to be 500 newtons. But there's also a force of thrust, we'll say. Thrust is just like, it's another name for a push force, but that would be provided in this case by the tail of the shark pushing against the water. So the thrust force, we'll say that's 1,500 newtons. So now in the purple, the x-axis here, x does not always have to be purple, but just in my diagram it is, we have left 500 newtons and right 1,500. How can we add those up? Well, 1,500 newtons plus, it's in the opposite direction, so how can I indicate that in my math? If it's in the opposite direction of the 1,500 newton. What math? Yeah, we'll say plus negative 500 newtons. 1,000 newtons, but we have to indicate what direction? Yeah, it has to be in the same direction as the bigger one. So 1,000 newtons right. So this is the net force. And is this balanced or unbalanced? Well, the net force is only balanced if it's 0. So is this balanced or unbalanced? Unbalanced. All unbalanced forces cause what? Come on. Unbalanced forces always cause a change in motion. Called, what's another name for change in motion? What's another name for change in motion? Acceleration. Is the shark accelerating? Yes. In this case, we would say it's what? If it's whether it's stopped or moving right, if it's accelerating right, what do we call that kind of acceleration? It's doing what? Getting faster. Getting faster. Do you see how a model like this is used? The objective was to model forces. Does anyone have questions about how a model of forces like this is used? I'm going to, without giving away too many answers, I hope, I'm going to show you some of what's on your test. One thing that you're going to be doing 2 long-form problems about is this guy pushing a box with a model of forces. And on the other side is another model of forces. These guys are lazy, so they just use boxes, whereas I use sharks and pigs and stuff. But it works the same way, okay? This is sometimes called a free body diagram, sometimes called a force diagram. but this is how we indicate, this is how we model forces on an object. You guys have questions about that at all? So I hope you understand balanced and unbalanced forces. I hope you understand acceleration, motion, and velocity, and the kind of units we use to measure force. Questions? This felt a little like pulling teeth, but that's okay. We'll work on it. Maybe when there's other people around, it'll feel better in the future. Bye.